Hello, my name is Burke Rosen, and this is the first lecture of the module on digital signal processing for the course Mathematical Foundations of Computational Neuroscience. Before I begin, I'd like to thank Stacy Kornikova and Scott Cole for their work on an earlier version of these lectures. This module is designed as an introduction into the theory and practice of neural signals analysis. And these types of analyses are very useful if you want to break apart your signal into its component parts and see what each part does or how it acts. You can see an example in this subplot over here where we have the frequency profile of our signal in two time windows. So we have the power represented as a t-statistic at every frequency between 0 and 100 hertz. And we can see that the profile of activation is quite different in these two time windows, which may very well be interesting. So how do we get at that sort of information? Well, in today's lecture, I will be covering the nature of digital signals, whether they are discrete or continuous, and talk about sampling theorem. I will then cover periodic signals, including just basic sinusoidal properties, and representing sinusoids as complex exponentials. That will transition us into the Fourier transform, and both its construction and its use. And I'll finish by talking about time-frequency trade-offs. So first, let's talk about digital signals. So we're familiar, most physical quantities are continuous or analog, and most of the math we learn is also continuous. And for these sorts of quantities, the differences between values can be arbitrarily small. As a metaphor, in a grocery store, when you buy ground beef, you can get it at any amount you'd like. You can get 6.35 pounds or 6.3521 pounds, assuming their scales are accurate enough. And if they're an analog spring scale, they are. But digital signals, which we must store in a computer, are discrete. Their resolution is finite in both time and amplitude. And in our metaphor, an example of this would be eggs. Ignoring the fact that we typically buy them in dozens, they're discrete because you can only buy a single egg. You can never buy half an egg or a third of an egg or 0.37 eggs. And the signals we're recording most of the time are going to be analog, but when they're stored in our computers, they become digital. Here's an example here. The blue trace is the original analog signal, and the red trace is its digitization. This is amplitude, and this is time. So this is a fairly coarse digitization. Our temporal resolution is determined by the distance between the grid marks on the x-axis, and our amplitude resolution is determined by the distance between the grid marks on the y-axis. Each tick here is a sample. So that's a value recorded. And the rate at which we acquire values is the sampling frequency, or sampling rate, denoted by Fs or f of s. In hardware terms, the device that does this transformation is the analog to digital converter, or ADC. So if you see that on your rack, that's what it's doing. In terms of mathematical notation, continuous functions are normally denoted by parentheses, whereas discrete functions are denoted by the square brackets. So the sampling rate at which we acquire our data does put limits on what kinds of information we can extract from the data. And specifically, the Shannon-Nyquist sampling theorem states that we must have at least 2 samples per cycle of the highest frequency data in our highest frequency information in our data. Therefore, our sampling rate has to be at least double the frequency of our fastest oscillation. This is expressed mathematically if f of s must be greater than or equal to 2b. So here is the example of a sufficiently sampled signal. So this signal is just a sinusoid. We have 2 samples per cycle, and we can accurately represent the signal. If you undersample your data, which is to say you have less than 2 samples per cycle, you will end up with aliasing, which is a type of artifact. And it's called aliasing because it results in a situation where your digitized signal may represent more than one actual signal. And here's an example of it in this figure. So we have the blue trace again is our original signal, but this time we've undersampled it. We have less than 2 samples per cycle. And that results in this orange trace, which A, is not very representative of the signal, and B, you could imagine other blue traces that would have this same digitization, the simplest case being a blue trace that was the same as the orange trace. You want to avoid aliasing, and therefore, when you collect data in the hardware of the data acquisition system, there's always an anti-aliasing filter, which limits the highest frequency of the data before it gets digitally sampled. And after data acquisition, the Nyquist limit is something important to keep in mind if you ever change your sampling rate by upsampling or particularly downsampling your data. And finally, I'd like to note that while the theoretical limit is twice your highest frequency, in practice it's better to use at least 2.5 and often greater for several reasons. The real signals are not as stationary as the ones I've drawn here, which is to say that the statistics of the signal drift at least a little bit over time. In addition, we are typically interested in the not just in the frequency information, but in the amplitude information. And if our samples don't fall exactly on the peaks and the troughs, then we're going to be underestimating our amplitudes unless we have sufficient sampling. So let's do a couple of short exercises with the Nyquist limit. If I'm interested in a 40 Hertz gamma burst, what must my minimum sampling rate be? Well, I know that my Nyquist frequency is equal to half my sampling rate, or my sampling rate must be twice my Nyquist frequency, and I'm interested in a 40 Hertz signal, so I want my Nyquist limit to be 40. And so my sampling rate must be at a minimum 80 Hertz, although, like I said, it's usually better to have some margin on that, to be more conservative. We can run this logic backwards. Let's say your given data, say clinical data, with a sampling rate of 256 Hertz. What is the fastest oscillation it makes sense to investigate in that data? Well, again, we go through it. So the operation is fairly simple. If we have our sampling rate, we end up with our Nyquist frequency, and thus it is really only advisable to look for oscillations up to 128 hertz in these data. So that is digital signals, and in particular, we're interested in oscillatory signals, and oscillatory signals are composed of sinusoids. So let's review some basic sinusoid properties and nomenclature. A sinusoid, like the one here, has a duration, which can be termed in numbers of samples or in seconds. So a periodic signal, in a purely mathematical sense, is infinite. It has an infinite duration, but in our computers, of course, we have no infinite signal. The amplitude is the distance from equilibrium to the peak of the sinusoid. The period is the number of samples, or the time in one cycle, so seconds, for example. The frequency is the inverse of the period, so that's usually measured in hertz or cycles per second. And then there's two related concepts: the phase shift, which is denoted with lowercase theta and is measured in radians or degrees, is the shift of the signal on the x-axis away from sine in this case. And then there's phase, and this is usually used in regard to a single sample, so say this point right here. What is the phase at this point? And that is the point in the cycle at which that sample lies, and that is denoted with a lowercase phi, and it's also measured in radians or degrees. I said frequency was in hertz. That's the way it's typically measured, but mathematically it's often more convenient to think of it in terms of angular frequency, which is our normalized frequency. So if you take cycles per second, your standard frequency, you multiply it by 2 pi radians per cycle, and you end up with angular frequency in radians per second, and that's denoted by lowercase omega. And finally, there's 3 verbs which are good to know: amplify and attenuate. If you're a hi-fi enthusiast, you already know those. Those are to increase the amplitude or decrease the amplitude. And then truncate means to reduce the duration. So if you cut the signal in half and throw the second half out, for example. All right. So here we have a periodic signal. And as I mentioned earlier, periodic signals can be represented as the sum of a number of sines or cosines. This is very similar to vectors. A vector can be represented as the sum of smaller vectors. So, is this combined periodic function itself periodic? So we know this is periodic. We know this is periodic. Is the sum of them periodic? Let's look at these signals. So they have different amplitudes, which is denoted by these coefficients in front of the cosines, but that's not going to affect the periodicity. And they have different frequencies, 3 hertz and 2 hertz. And that will, if we look at the graph of this combined function, it looks periodic by I. And by I would guess the period is 1 second from this peak to that peak. But the rule for determining this is to look at the least common multiple of the periods of the composite function. So we know the frequencies. The inverse of that is the periods. So this function has a period of 1/3 of a second, and this one 1/2 of a second. The least common multiple of 1/3 and 1/2 is 1. Now, because they have an integer least common multiple, that means this combination is indeed periodic. And not only is it periodic, but its period is equal to the least common multiple. So the least common multiple is 1, the period of the combined signal is going to be 1, and that matches our intuition from just looking at the plot. And this is generalizable. It applies to any periodic signal, and you can sum really any number of sines and cosines. And this is the same construction represented a little bit more formally. So now we have a cosine and a sine. We have the coefficient in front of the sine and the cosine. And this is computed at a series of frequencies, and then we sum over all the frequencies. And the basic idea behind the Fourier transform is for a given signal to solve for these coefficients. So there's a GIF from Wikipedia which I think illustrates this conceptually rather well. We have our original signal in red. We break it into a series of sinusoids and compute the amplitudes or the coefficients of each one, and align them all up, and we get our Fourier spectrum of our original signal. And one further note: how many frequencies do we need to loop over in order to get a sufficient number? Well, there is a convergence. Where you have diminishing returns for additional frequencies. So here is an example of a Fourier synthesis. We have the signal we're trying to produce is a square wave, and we can start with one set of sinusoids, and as we add more, a second one, and a third, and a fourth, we get closer and closer to our desired signal. One brief aside is why are sinusoids special? We see them in nature, in many areas of physics, and they come up a lot in engineering as well. And why that function as opposed to a sawtooth or a square wave, which are perfectly good functions. And the reason is, well, there's several, but the first one is that many natural processes, and some artificial ones, follow Hooke's law, which was originally developed in springs, and states that the force on an object is proportional to its displacement. And when Hooke's law is true, the equations which describe the object's position and velocity are linear differential equations. Or more formally, sinusoids are the eigenfunctions of linear time invariant systems, which is to say that they're functions for which the output is a scaled version of itself. So let's illustrate that a little bit. Here we have our spring system and our object, and plotted are the object's velocity and position. It's forming a circle in this two-dimensional phase space. And if we add time to this and plot that trajectory, we end up with our sinusoid. A second, but not separate, reason is that sinusoids with different frequencies are orthogonal. And if you have a set of sinusoids with different frequencies, they form an orthonormal basis. And that is to say that the dot product of sinusoids with different frequencies is 0. And to compute the dot product of these sinusoids, we take the integral of the product of the functions. And because the frequencies are different between 0 and 2 pi, or any integer multiple thereof, including infinity, they are on opposite. Have opposite signs just as often as they have the same sign. Therefore, their product will have this symmetry to it, and the integral will always be 0. So again, we have a sum across many frequencies, a cosine and a sine. We're solving for our coefficients. Periodic signals have an alternative notation as complex exponentials. So this comes from Euler's formula here. E to the it equals cosine of t plus I sine t. And this formula can be arranged to form these identities. The proof of Euler's formula is talked about in one of the links I'll provide at the end of this lecture. So instead of having a sine and a cosine, we can get a simplified, in many ways, construction like this. We have e to the I omega t plus phi. And the geometric interpretation of this notation is shown in this three-dimensional phase plot. So we have time, we have an imaginary axis, and a real axis. And our oscillation is traveling through this space. And if we project that oscillatory activity onto the real axis, we get our cosine, and that makes sense because cosine is the real part of the signal. It does not have the I in front of it. If we project it onto the imaginary axis, we get our sine. And it's spiraling through time. So this sum that we've seen a few times now is more elegantly expressed in complex notation. And now we have just a single coefficient at each frequency, and we don't have to worry about the sine and the cosine separately. The Fourier transform, the continuous form, is shown here, and this is a way of transforming the signal. So we take our original signal, multiply it by e to the negative omega t, and then integrate over it to get our transformed signal in terms of frequency. The discrete form is shown here. And the discrete form is more relevant to us typically because we are using digital signals, but it's quite similar, except instead of omega t, we have 2 pi k little n over big N. And to unpack that, we have 2 pi radians times k is our frequency, times n, little n, the number of samples in a cycle, and divided by big N, the total number of samples. It's really saying the same thing, it's just the discrete interpretation. And when you perform the transform, the vector that you're left with is complex, and you have both real and imaginary components. You can compute the amplitude by taking the sum of the squares, or the norm of the real and imaginary component in the geometric interpretation. Another way to look at the Fourier transform is as a linear map between the signal as a function of time and the signal as a function of frequency. So in this view, we have our original signal, we have our Fourier spectrum, and then we have this matrix operator, which does the conversion. So this is the tight representation of that operator, where omega is e to the negative 2 pi over big N, which again is just the number of total samples. And if we expand this out into what the matrix would look like, it looks like this. Now, you've probably heard of FFT, or fast Fourier transform. This is how a computer actually computes the Fourier transform. And when it runs its inverse, it does the IFFT. And the way that fast Fourier transform works in concept is to take advantage of the symmetries in this matrix to perform very fast operations on only parts of the matrix at a time. And it's aided by the fact that if your signal has a number of samples equal to a power of 2, you can cut the signal in half many times. Higher level functions which do an FFT for you, these days will not force your signal to be in a power of 2. It will just pad the signal until it reaches a power of 2. So let's look at some examples of Fourier transforms. So here we have a sine and cosine function, and here are the original signals. And here's the real part of the Fourier transform, the imaginary part of the transform, and the amplitude. And you can see that the Fourier transform of a sine has no real component, and the Fourier transform of a cosine has no imaginary component. And that makes sense, recalling Euler's formula that the cosine represents the real part of the signal and the sine the imaginary part. And because these are pure tones that contain only one frequency, when we do the Fourier transform, we have a single positive peak in the amplitude. Now, it's curious that this is mirrored by a peak in the negative frequency range. And what is a negative frequency, and how does that make any sense? Well, sines and cosines don't really make sense with negative frequencies, but complex exponentials can. And if we want a geometric interpretation of that negative sign, one way to look at it is if we go back to this phase plot. Before, when we had a positive frequency signal, this spiral was traveling counterclockwise through time. For a negative frequency, it could be said that the spiral is traveling clockwise, in the opposite direction. And that's where our negative frequency comes from. A couple more examples. If we have a square wave, we end up with a sinc function. If we have an immediate rise followed by exponential decay, you get something like this. Gaussian is an interesting case because the Fourier transform of a Gaussian is a Gaussian, which is useful. If you have a delta function, just a single point above a sea of zeros, that is equivalent to equal frequencies at equal power at every possible frequency. So it's sort of the reverse of a flat line, which would be zero power at all frequencies. All right, so the Fourier transform can get our signal into a frequency basis, but it's not the final product of our analysis most of the time. And so a few more steps we normally do are to convert that into a power spectral density, which can then be plotted as a periodogram. And to get a PSD, or power spectral density, from the Fourier spectrum, we take the absolute square. The plot of the PSD looks something like this. So you have frequency, or period, that's where periodogram comes from, in the x, and you have power in the y. Here it's being expressed as microvolts squared. That's the same square here. And it's been normalized by Hertz. And it's been plotted in semilog, which is quite common for a periodogram. So this underlying trend here is typically known as the 1/f noise, and then the bumps on top of it are the oscillations. And we know this data was collected in Europe because it has a particularly strong oscillation at 50 Hertz. This has the line noise left in it. One thing to keep in mind when computing the power spectral density is that the power in the Fourier transform should be equal to the power in the original function, a truism known as Parseval's rule. And if we're not careful, we can violate it. So here's a snippet of MATLAB code I used to compute a power spectral density. So I had a signal x, and it has n samples. I compute the FFT. I take out the first half of the FFT, because if you recall our examples, the first half of the Fourier transform is just the negative frequencies that I'm not interested in. And negative frequencies don't provide any additional information for real signals like those we record in nature. But they do count towards the power total, and therefore I have to apply this scaling factor when I'm computing my power spectrum. So the PSD is a fairly noisy signal, but there are ways to clean it up. A very common way is Welch's method. And Welch's method works by dividing up the total signal into windows, computing the PSD of each window separately, and then averaging them together. So the trade-off is that it reduces the variance, but it costs you spectral resolution. And you can see an example here. This is a periodogram. The original periodogram is in black, and using Welch's method, you get something in red. Much cleaner. Another one which you might run into is called the multi-taper method. I'm not going to go into it in detail, but just say briefly that it's an extension of Welch's method, and it uses adaptive window functions. So window functions are often applied before computing the FFT because they increase the dynamic range of the transform. And a window function is just a function you apply to your data when you cut a chunk of it. So applying no window function is equivalent to a rectangular window or a boxcar, so it's uniform across the window. And this is the Fourier transform of a pure tone with this window function applied to it, and the dynamic range is small. Whereas if you apply either of these two closely related window functions, you get a much better dynamic range. The most commonly employed are the Han window and the Hamming window. And here's a MATLAB example of using one. And it's a pet peeve of mine whenever you see Hanning, because the guy's name was Han, and this guy's name was Hamming. There's no such thing as a Hanning window, but that's just my own personal proclivity. So let's do some exercises. Let's say I want to analyze my data in the frequency domain, and I'm interested in oscillations up to 120 Hertz, and I want to be able to distinguish oscillations that are only a half Hertz different. What must my signal acquisition parameters be? Well, first let's figure out what my sampling rate has to be. So this is a review from before. I know that my sampling rate has to be double the highest frequency I want to record. So I need to be sampling at least 240 hertz. What about my frequency precision? Well, I know that my fmin is the inverse of my duration. I want half a hertz, so I need to record for 2 whole seconds in order to achieve sufficient frequency resolution to distinguish signals that are only separated by half a hertz. And of course, these are minimums, and in reality, I'd probably want to be more conservative and have more time at a higher sampling rate. Second exercise. Is it possible to distinguish separate oscillatory peaks at 8 and 12 hertz and a signal consisting of 200 samples collected at 1,000 hertz? What parameter must be changed and how? Well, my fmin is equal to my sampling rate over my total number of samples. And so I collected my data at 1,000 hertz and I have 200 samples. So my fmin is 5 hertz. Which is greater than the difference between 8 and 12 hertz, and so I cannot distinguish those signals with these data. I need to collect data for a longer amount of time. I need at least 250 samples. It also means that if I have long data, but I'm interested in how 8 hertz signal and the 12 hertz signal change independently over time, my time resolution is limited to a quarter second. So in summary, I went over what digital signals are. I talked about sampling theorem. I talked about periodic signals, both their basic properties and their complex exponential representation. I then went into how we arrive at the Fourier transform and what we do afterwards with power spectral densities and time frequency trade-offs. So here are some useful links. This is a series of videos on a mechanical Fourier analyzer from, I think, the turn of the century. And it not only is it very interesting, but I think it gives good intuition for the Fourier transform. This is a good video on the proof of Euler's formula and Euler's identity. And this is some MATLAB documentation related to power spectral densities. Thank you. In the next lecture, we'll be covering time frequency analysis and making use of what we learned about time frequency trade-offs.